Okay, so this is just for the knowledge purpose. I have written that if somebody is curious about how the contact potential can be measured using voltmeter, so um, that is not possible, right? नो कोई आवाज नहीं आ रहा, क्या चक्कर है? ज्यादा क्लास हो गया क्या?
नो सर, सुन रहे हैं सर।
So अभी जो बताने just now what I am going to say is a very important thing, that the current components in a PN diode. If you have followed the discussion, then you can easily understand it, that what are the current components in a PN diode. See, there can be two types of currents in a PN diode. One is due to the diffusion of the charge carriers, another is due to the drift drift of the charge minority charge carriers, right? So there can be mainly two components. So as you know that we have seen that when we have not applied any bias, right, how a PN junction behaves. But means we can say that that condition is called as an at equilibrium, right? And when we applied a forward bias, how the excess charge carriers injected into the p type and n type, right, that leads to the excess current flow. So we are going to see that. So so we discussed that when a forward bias is applied to a diode, holes are injected into the n side and electrons into the p side. Is it true? So under low level injection conditions, such minority currents are due almost entirely to diffusion. So you know that when you apply a forward bias, mainly it is due to the diffusion, because the drift current is very negligible. So that can be neglected also, right? So the whole diffusion current in the n-type material, I am coming to this line later, you may not be following. See what it is written over here. This is a diagram taken from Millman Helkias, right? Please focus. You can easily understand it. Don't. There is nothing complex into it, right? So what is the meaning? Like when we are writing IPN. IPN, first see, this P stands for charge carrier. That means current due to holes, right? The whole current in the n type, right? The whole current in the n type of material, right, at the n side. Similarly, INP, the electron current at the p side, right? So once we read it, it is read like this. I just want to show you, okay, I'll come to this diagram. So let us start from the basic that we discussed. So this is basically a p-type material. This is an n-type material, and when you make a p-n junction, this is basically the depletion region, right? This side there are donor ion. This side this is acceptor ion, and when you applied a bias, forward bias, right, connecting positive terminal of it to the p side and negative terminal to the n side, right? Then you know that what are the changes occurs in case of a uh, this band diagram that we have seen when uh, this was the energy band diagram when there was no bias. If you remember, is it so? Is it not? Because this band gets this energy band diagram, this slope gets band because of the electric field, right? Because of the electric field, this banding comes, and we have a contact potential between N and P region, that is equivalent to Q into V0, V naught. This is I am talking about when we were, uh, so this is the Fermi level, right? And this is what the conduction band at the N side, and this is what the valence band at the N side. This is the valence band at the P side, and conduction band at the P side. So you know that uh, when the doping occurs, this the energy level, right, that lies just the Fermi level, that is like once you add impurity, it is near the conduction band in case of a N type, and it is far from the conduction band. It is near to the valence band in case of a P type. Do you remember that? Please
Yes, sir.
respond.
Yes, sir. Yes, sir.
So this is basically a contact potential Q into V naught, right? So once we apply
Yes.
a bias, right, forward bias, then what happens? This band diagram changes because the contact potential is, the barrier potential is reduced by this applied bias that we all know, right? So there are two types of current, uh, basically diffusion, as I said earlier also. Uh, the current is constituted by both the charge carriers, because when you connect this battery, the holes are injected and the electrons are injected to this side, right? And these electrons will move to, will try to diffuse. When the barrier is lower, they will try to diffuse to this side, and the holes will try to diffuse to this side, and finally that will lead to the flow of the current. So electrons will try to diffuse from N to P, and holes will try to diffuse from P to N. So current due to the diffusion of the, uh, one is the diffusion of the charge carriers, right? And there are majority charge carriers, like you can see that the electrons are the majority charge carriers and holes are the minority charge carriers in this region. Similarly, uh, holes are majority charge carriers in the P region and electrons are the minority carriers, right? So now I am just uh, changing it, right? Now, oh, if you, this diagram is not clear, I can draw it again. Um, so basically the current which occurs, that is due to the diffusion of the minority carriers. Okay, so and basically these electrons and holes, this constitute the current in the PN junction. Electrons are the minority carriers at the P side and holes are the minority carriers at the N side. Up to this, is it clear?
So,
Okay. So now
Yes, sir.
yes, sir.
just see this diagram. There is nothing like very complex. So what I am writing here, that this is P side. So what is in majority here? Please,
Holes.
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 So this is what I have plotted on a log scale. That is, I have plotted the concentration of charge carriers, right? So this is what uh, the depletion region, right? This is what the depletion region I am saying at the junction. This is what the junction, right? So in case of an equilibrium, when there was no bias applied, presently we are considering when there is no bias applied. So this is what the concentration of holes at this side. So this is larger, this concentration is higher. So from there, from P side, crossing this depletion region, some of the holes reaches at the N side. So they are here as minority charge carriers, PN naught. So these are the holes reaching to the N side, right? So these are the minority charge carriers. Similarly, there are electrons which are in majority at the N side. They will try to diffuse to the P side, right? And will reach as a minority charge carriers, because only very few will be able to make it to this side, right?
Yes,
Already,
sir.
so that is the minority charge carriers at this side, right? So this is the scene which when they cross the junction, they are at the junction. We are say talking about at the junction. Now when you apply a bias, a forward bias, then what will happen? Can you say what will happen? Because अभी आपने जब bias लगाया यहाँ पे तो क्या हो रहा है? पहले there was no bias, right? So there were at equilibrium, or you can say when there was no bias, there was some the concentration was lower of the minority carriers का concentration क्या था? Lower था, right? But once you put the battery, this concentration will increase because one more, more charge carriers, because the barrier is lower, so more number of charge carriers will be able to cross the junction, because once you apply the forward bias, this barrier will go lower, so more number of electrons will be able to come to this side, right? As in case, as compared to the previous case. Similarly, more number of holes will be able to cross and will reach to this side, right? So this is basically, these are what? These are
If I'm being
okay, let me redraw it. I'm drawing when we apply a bias, right? When we apply a bias, let me draw the interface. So once you apply a bias, this is what the, so suddenly there will be more charge carriers will be there, excess will be there, and they go like this. So this excess of charge carriers, right? This excess of charge carriers occurs due to, these are the you can say these are the excess concentration of holes on n side. Similarly, excess concentration of electron at p side. Similarly, because of the bias applied, uh, there will be a rise in the electron in the holes concentration at the n side. So this is pp, right? So this excess of holes, ऐसा होगा कि नहीं होगा ये बताओ आप. So these are extra holes. These are extra holes at the n side. These are extra electrons at the p side, right?
Yes.
Where this pp is nothing but your Na. What was Na? Na was acceptor concentration. So pp is nothing but your acceptor concentration, and this np naught. This np naught is nothing but your, this is what, the minority carriers at the p side, right? So this is equivalent to Ni square by Na. Ni square by Na, which is, Ni square is what? Intrinsic concentration. Or Na is acceptor concentration, right? Similarly for the p side, similarly for the n side, Nn will be equal to Nd and pp naught, which is, sorry, P, Pn naught will be equal to Pp naught will be equal to Pn naught will be equal to Ni square by Nd, right, at the n side. So these are the formulas which are taken from the semiconductor physics. Okay, we are not going into the depth of these things, but just you must be knowing also these things. If you are not knowing, then please assume it. Okay, because we cannot go into that side, right?
Excuse me, sir.
Yes, yes, please.
If we do the forward bias of a semiconductor, it will not happen at the equilibrium that minorities are electrons in the inside and majority of holes in the minority of holes at the p side and majority of electron at the p side. And
Right.
vice versa.
Just let me answer it. See, at equilibrium, when there was no bias, please listen carefully. When there was no bias, generally this is the p side is having access or the majority carriers as holes, n side is having a majority carriers as electrons. So these holes which are able to cross this barrier and reaching this n side will become minority carriers here, because here the access is of electrons, right? Am I clear?
Yes, sir.
Similarly, the electrons coming from n side to p side are becoming the minority carriers, right? So we have discussed only this thing only, that when at equilibrium, when there was no bias, right? This
When my question is
so,
for forward bias.
huh?
My question is for forward bias.
I'm coming to that point, right? What I'm saying that see, just try to understand this part, that when you have applied no bias, then at that time this concentration is less, right?
Yes.
But when you apply the bias, forward bias, you will receive more number of electrons at the p side, as you will get an excess electrons at the p side. Similarly, you will get an excess holes on the n side. Is it clear? This part is clear.
Yes, sir. Yes, sir.
Okay, then what is your doubt?
जल तो मान पी साइड में माइनॉरिटी होल्ड हो जाएगा और एन साइड में माइनॉरिटी ये इलेक्ट्रॉन हो जाएगा सर एक
माइनॉरिटी
टाइम के
इलेक्ट्रॉन
बाद
कैसे हो जाएगा?
जल वो होला ना डिफ्यूजन ट्रांसफर ऑफ इलेक्ट्रॉन्स फ्रॉम एन टू पी and p to
but
n
but 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 new charge carriers are also coming, no, right?
or
New charge carriers are also generating, right?
okay yes
So that always electrons will be in majority at the n side and holes will be in majority at the p side, right? Then the okay, so this much I want to say first, that this excess electrons, right? This excess electrons will lead to uh, so these extra holes and electrons are responsible for current, because the barrier is reduced. Because of this the barrier is reduced, they are to allow the movement of charge carrier. So this extra holes and electrons are responsible for current, right? Now coming to this diagram, this is the same diagram, okay, the same diagram which I have explained, I have drawn, right? This is what the same hole concentration at the p side, which goes here at the junction and becomes minority carriers, right? So this is what, when we are applied no bias, right? When there is no bias. But when you apply forward bias, there is some excess electrons you will get, that is Pn node, right? Some excess electrons you will get, that is Pn node. So excess holes, sorry, that will be Pn node. So that is what it is written, Pn0 minus Pn0 will give you the how many access holes you have received at this side because of the uh, forward biasing, right? Similarly, these electrons, please do ask if you are not following, or please stop me if you are not following. So these are the electrons which are crossing the barrier, and NN node, this becomes uh, holes at this side, this becomes minority carriers at this side, electrons at the p side when there is no bias, right? Minority carrier concentration when there is no bias. And this is what this shows, the excess electrons, right, because of the forward bias when you have crossed, when you have applied a forward bias, right?
Yes, sir.
So I hope there is nothing no problem in this. So this is a majority carrier concentration, this and this, and this is a minority carrier concentration, and this shows the excess electrons and holes at the n side and p side respectively, right? And this is what the same thing is shown for the current density, right? uh, the total current is constant throughout the device, so that is basically the total current is constant, right? The total current is constant. That will be basically, we will see also that it will be a combination of the current density due to holes, majority carrier current, and minority carrier current, right? Because of the recombination, there will be some different drift current. So diffusion plus drift both will be there. ड्रिफ्ट क्या होगा, ड्रिफ्ट करंट बहुत छोटा सा होगा, क्योंकि ये जो चार्ज कैरियर्स यहाँ आ रहे हैं, ये जो इलेक्ट्रॉन्स यहाँ आ रहे हैं, ये क्या होगा, जंक्शन पे तो काफी सारे होंगे, लेकिन धीरे धीरे ये क्या हो जाएंगे, once they move away from the junction, what will happen, क्या होगा, नहीं समझ रहे हो या नहीं समझ में आ रहा है, मुझे लगता है. See, just try to understand this part, that these these holes which are injected into the n side, right, they are coming over here. तो यहाँ पे at the junction जब आप बात करोगे तो वहां पे क्या होगा, they will be more, but as they move away from the junction क्या होगा, बताओ, they are very less in comparison to the
Yes.
majority charge carriers electrons here in the n side. And what will happen, they will get recombined and they will be lost, right? As they move away
Yes,
from the
sir.
junction, they will be lost, right?
Yes.
So that,
Yes, sir.
so that thing only you have to understand, that this the excess charge carriers which are coming into this, diffusing into this region, once they move away from the junction, they will get destroyed, right? Because they will get recombined and they will get destroyed, right?
Yes,
Is it
sir.
clear?
Yes, sir.
So now so we are just doing a derivation of this, right? The same thing, as you know that the rule of Boltzmann relationship, you know that this we have proved yesterday, Wp upon Wn equal to Na upon Nd yesterday, because the area, if you remember, we proved it. So so as you know that the differential density of holes and electrons in the Pn region, the Boltzmann relationship may be made applicable. What it says, Boltzmann relationship, N1 equal to N2 exponential V21 by Vt. What is N1? N1 is density of particles in region 1, right? N2 is density of particles in region 2,
In region 2.
right? And what is V21? Potential energy divided by voltage of region 2 with respect to 1, right? Voltage of region 2 with respect to voltage region 1, and divided by this thermal voltage Vt. So Vt you know, kT by Q, or it is at room temperature, its value is 26 millivolt. So we are using this relationship only, right? And we will be finding out the concentration of electrons at the junction. Okay, extra electrons injected to the p side, and extra holes injected to the n side. So the concentration of electrons at the junction, so you can see that np naught, which is extra electrons injected to the p side, and pn naught is extra holes injected to the n side. Just consider this diagram. Okay, so np naught, extra holes injected to the p side, and pn naught, extra holes injected to the n side, right? So we can write just from the Boltzmann relationship. Just now we have discussed that n1 equal to n2 exponential V21 by Vt. So as per that, so I can write this np naught, which is extra electrons injected to the p side, n1 reason 1, equal to nn naught, because nn naught was the majority charge carriers at the n side. Please respond.
Yes, sir.
Yes, sir.
So this is the majority charge carrier, majority carrier concentration, and this is what the minority. So we are saying n1, n2 exponential of minus of E VO minus VD. VD is the applied bias potential, that right, VD divided by KT. Similarly, the excess holes injected to the n side, we can write PP0 is the majority concentration of holes at the P side, exponential of minus of E VO minus VD by KT. So these are excess electrons at P side, these are excess holes, okay, at the n side. So basically these are minority carriers, right? So you can see this minority carriers concentration is directly proportional to the VD. Can I say this? Because if you see, this KT is a constant, KT by E is a constant, right? These are constant. VO is what? The contact potential, right? So that is also we can say is fixed. So we can say that this concentration is directly proportional to the applied bias. As you increase the bias, there will be क्या होगा? If you increase the bias, what will happen?
More charge will flow from one side to the other.
Right. So minority carriers will minority carriers will increase, right? This concentration will increase, because more, once you increase the potential applied potential, what will happen? The potential barrier will get down,
Decrease.
right? So the more charge carriers can diffuse to the other side and will result in excess electrons and holes at the n and p side, right? So higher will be the value of VD, lower will be the barrier, and higher will be the number of electrons and holes, right?
Yes, sir.
So if we put VD equal to 0 at equilibrium, so that should satisfy the that So as you can see that these electrons and holes which are in minority carriers, as I told you that they will be there at the junction, and once they move away from the junction, what will happen? They will get recombined and will destroyed, right? So because there are majority charge carriers, so they will get recombined with them and will get destroyed. So if we and that basically satisfies the law of the junction, that says that how the junction behaves when you apply bias, right? So I can write this if I say at equilibrium VD equal to 0. So this reduces to Pn naught will be reduces to Pp0 exponential minus of E V naught by kT. So as I said that that when the charge carrier moves away from the junction, they get recombined and get destroyed. So now the question comes that how long these charge carriers will be can make it in this region, right? So for to see that we need to define a diffusion length, that how long they can be there, right? Diffusion length of the minority carrier diffusion, like, so we define a diffusion length here. Okay, so diffusion length LH or LE, diffusion length for holes, diffusion length for electrons, right? This is a minority carrier diffusion length, and there is a diffusion coefficient. So basically this is defined as LH equal to root of DH into tau n. Tau n is basically carrier lifetime. It says about the time hole or electron travel in the material before they recombine and destroyed, right? So this basically says that what will be the length, like when it is moving away from the junction, that what will be the diffusion length, means how long it can move away, right, before getting destroyed. So that diffusion length is LH. So that is defined as DH tau n. So tau n is a carrier lifetime, which says about the time that how long the electron and hole can travel in the material before they recombine and get destroyed, right? And this is what DH or DE is called as a destroyed means like vanish, no, like this recombine के बाद क्या होगा, what will happen, will it be there to move,
खत्म हो जाएगा sir.
खत्म हो जाएगा, right? So this and this is another term, that diffusion coefficient, which is related basically to the mobility of the charge carriers. So DH or DE, so you can see that KT mu H upon E, D is KT mu E upon E. So the mu H and mu E are the mobilities for holes and electrons. So I've just written an example that if mu H is given as 450 centimeter square per volt per second, and mu E is given as 1350 centimeter square per volt per second, in case of intrinsic silicon, right? What will be the diffusion length? So if I have calculated this, the diffusion length comes out to be carrier lifetime comes out to be 10 to the power minus 9 seconds or nanoseconds, right? LH will be equal to 1.08 micrometer. So you can see that that after going from moving away from the junction of 1.08 micrometer, this will get destroyed, right? So this is what the diffusion length says. So when we see, is it clear or not?
Yes, एक बार फिर से बता दो.
जस्ट बता रहा हूँ. ये यहाँ तक क्लियर है, ये जो excess holes, excess electrons, just we have written from the Boltzmann relation, is it clear?
Yes sir.
So as you can see that it is directly this excess concentration is directly proportional to this applied bias Vd. So as you increase the bias, what will happen, more charge carriers will be able to reach to the other side, because the barrier potential will get lowered, right? And more charge carriers will be will make through to the other side, and this concentration will increase. So as you increase it, more charge carriers will reach there, right? So once the charge carriers have reached the junction पे तो बहुत ज़्यादा होंगे, but once they move away from the junction, once they are moving away from the junction, what will happen? Here, they are in minority here, right? They are in minority here, and once they are moving, once they are here, there are majority charge carriers. Suppose if I take this side as an example, these are the holes. Holes are in minority. So once they are
Colin,
moving
Samir,
away from the
it's 20.
junction,
the New York Times said about our phone. Here's what the Wall Street Journal said about our phone, and here's what MKBHD said about our phone. And those will be the only quotes in the video. My parents would be like, "That's amazing."
Yeah.
I'm like, "Oh, cool."
Is that a source of revenue that's like...
I don't remember the name of it, but I just found an animated channel that has a whole bunch of videos about murderers, but they're all animated.
Oh.
So they'll like go through like a 20-minute history of a serial killer with graphic detail about how it all happened, but they're all like nice, friendly animations, which is kind of a weird
Only on
juxtaposition.
YouTube
Yeah.
would that happen.
I think so.
Yeah.
So whatever that channel's called, I'll probably have to find that and pull it up. But yeah, I found
That's
some
good.
of that.
That's
lately.
really good.
Yeah.
That's the strange channel you've subscribed to most
I
recently.
haven't subscribed,
Okay,
but
you're not
they're
fully there
all
yet.
over
Yeah.
my homepage, so I might as well be subscribed.
Wow.
Yeah.
So minority carrier diffusion current. So that is LH is equal to DH root of DH into tau n. What is tau n? Tau n is called as the carrier lifetime. So this is the time where that defines that electrons and holes how travel in the material before they recombine. So this is the amount of time they will be moving in the material. Once this time is over, they will expire, right? So similarly, this diffusion coefficient DH or DE, it is given as this. Basically, it is related to mobility. This diffusion coefficient is related to mobility for holes and electrons. So it is written as kT mu h upon E, kT mu E upon E, where mu h and mu E are the mobilities of holes and electrons respectively, and their values, typical values for an intrinsic silicon is this. 450 centimeter square per volt per second. Similarly, 1350 centimeter square per volt per second. So I just took an example and calculated this diffusion length, which comes out to be 1.08 micrometer for just keeping it in this formula, right? I calculated because kT upon E is fixed, right? kT upon E is a constant, right? It's a Boltzmann's constant. It's a room temperature, absolute temperature. It's a charge on the electron. So from here, you will get the diffusion coefficient, right?
Yes, sir.
And and if you take this tau, that the carrier lifetime as this nanosecond, 1 nanosecond, then you get this diffusion length as 1.08 micrometer for holes and 1.9 micrometer for electrons.
Keiko
So
must be
this
very
indicates
upset about
that
the school
once
closing.
the charge carriers
That's
are
just it,
moving
sir.
away from the junction,
She's acting like she
after
doesn't
a
care.
distance of
Like there's nothing wrong.
1.08
Sounds
micrometer,
bad.
all the holes,
I've tried
the
to lift her
minority of
spirits
the
a bit.
N side will get
Romantic dinners,
destroyed.
long
right?
moonlit walks in the hollow suite.
Is it clear?
I
up to
even
this?
rearranged my work schedule so I could spend more time
Sure.
with her. Nothing seems to make a difference.
But now you have an idea.
So now what
Oh,
we will
yes,
see,
sir.
we will see
Um,
the
I'd like
concentration
permission
of electrons
to
and holes
convert one
as
of
a
the empty
function of
cargo bays into an
X.
arboretum.
X is the distance
I think Bay
that
21 would
takes
be
it
ideal.
from
The ODN conduits are shot,
away from the junction.
and the security
So like
systems
at
never
the-
worked anyway.
At this interface, right? Away
So
from
you're
the
saying
junction,
yes?
Ah,
that how
sounds
long
like it to me.
they survive, right? So away from the junction, we will see as a function of X.
Listen, there's nothing harder than knowing that the person you love is
Shall I
unhappy.
continue or you have a class?
And I know how important it is to do something about it. If one empty cargo bay makes Keiko happy, then I'm all for it.
तो थोड़ा सा और
I just hope it works.
बाकी है. ठीक है, we will do it in the next class tomorrow, right?
She
The remaining part
sacrificed her
we will
entire
do
career.